Okay, are there any questions before we get started?
What are we learning today?
I'd like to start a fast multi-code.
Okay.
Okay. But before I do that, I'd like to talk about something else, which is internal reference problem. Okay, we can illustrate this with a scalar wave equation. Say we want to solve a problem such as this one. P r equal to S of r. And let's assume that we are solving this problem in a cavity. And we put some source inside. You have learned from chapter 1 that this solution is unique, provided that it will not hit the internal resonance of this one. Okay, let's try to understand that slightly better today. And one thing I want you to note is that this Laplacian operator is positive. No, it's a negative definite operator. It's negative. And which means that if you convert this into a matrix system A dot X, this A is always negative definite, which means that all the eigenvalues are less than 0. So all the eigenvalues of the system is less than 0. We can prove this quite easily by saying that if I have this operator, and if I test this with its complex conjugate and integrate over the volume, say this is a volume that I integrate over, then I can do integration by part, saying that this is actually the same divergence of phi star grad phi is equal to grad phi star dot grad phi plus phi star grad phi. Okay, if I use this matrix, this vector identity, then I can rewrite this as being equal to the surface integral term. This can be converted into surface integral. Okay, which is this surface S. I'm sorry to use the same notation S. This means floor, this means surface. And then I have the second term that is remaining, which is this other term. Okay, so this will be the surface term minus that term. Okay, so you have dV grad phi, and this term is just equal to that. Okay, so this operator is the same as that. And if you have a boundary condition such that phi equal to 0 on S, or n dot grad phi equal to 0 on S, then the surface integral will appear. And then this thing is always less than 0 because of this negative dt. So you can easily prove that this operator is negative definite, which means that the eigenvalues of the discretized Laplacian operator is always negative definite. But then k square phi is always positive definite. If this is the real number, this is always positive definite. So this thing together, this is positive definite, this is negative definite. Together becomes indefinite. So Laplacian operator plus k squared is indefinite. Indefinite means that sometimes the eigenvalues can be negative, sometimes the eigenvalues can be positive. That's what it means by indefinite. And that gives rise to a problem, which means that this operator is indefinite. So if we convert this into a matrix equation, A dot X is equal to B, sometimes this has positive eigenvalues, sometimes this has negative eigenvalues, and sometimes it has 0 eigenvalues. And when it has 0 eigenvalues, you cannot solve this problem. When this thing has 0 eigenvalues, this matrix system is not invertible. This is known as the internal resonance problem. And gives rise to numerical difficulties in a lot of examples. And one example is just the simple solution of solving this integral equation that we have formulated. Last time we said that if you have a scatterer, acoustic scatterer, to make things simpler, then you can formulate an integral equation that looks something like this. Where S is the surface, and you put surface charges on the surface, you integrate, and then you discretize it. But it turns out that this equation does not always have a unique solution if this is a dynamic problem. Dynamic problem means that it corresponds to this kind of equation, this kind of Green's function, because there exists a solution where this is true. There's a null-space solution. This null-space solution exists due to internal resonance. So this equation becomes non-unique when you hit the frequency of the structure that it resonates. And this gives rise to air conditioning. And there are ways to overcome this kind of thing. Okay, I will not talk about how to overcome them. It's discussed in the textbook. But you also encounter this not only in acoustics problem, but also electromagnetic problems. And the physics is very much the same. The physics is that you come up with a structure, you shine a wave onto it. There could be interior solution, because when you solve this kind of problem, you only impose the equation on the surface. So you're actually pretending as if there's a thin shell of scattering, a thin shell of scattering rather than a thick scattering. So in the electromagnetic case, we solve the problem as if there's also a thin shell of a scattering. Okay, a thin shell. And this thin shell is not perfect. It does not, for instance, it does not model the extinction theorem exactly. So the field cannot be entirely extinct inside. When we formulate this equation, we use extinction theorem to say that the field is completely extinct inside. And the electromagnetic case, the same thing. When we solve this equation with a surface current source on the outside, we assume the extinction theorem holds true exactly. But that is not true in the numerical world when you approximate this current with an approximate current. So some leakage will leak electromagnetic energy into this scatterer and give rise to internal resonance solution. So there will be currents building up because this is a cavity. If you hit this resonance, and then there will be interior currents building up on the interior surface of this scatterer. And since this cavity is not a perfect cavity, sometimes this current also radiates. Okay, give rise to internal resonance problem. And if you look at the radar cross-section of this geometry, you find that it's not accurate when you hit an internal resonance problem. Okay? So this is the case. Any questions on this?
What if you use the volume integral equation instead of surface?
Volume integral equation will not have this problem. Another way of avoiding this internal resonance problem is to assume that the scatter is thick, have a certain finite thickness. Okay. Then you model this with redundancy. You require the field to be extinct, not only on the surface, but a tiny region around the surface. That models a thick scatterer. And you find that in this case, there could be no internal resonances. Okay. The same thing too. And there are people who suggest putting posts, shorting pins inside this scatterer so that it shorts out the electric field inside so that the resonant modes cannot exist inside. And then you will remove this internal resonance problem. Okay?
How do equations vary when you have a thin shell and a thick shell?
Oh, in that case, you will impose this not only on S, but maybe a number of S, S1, S2, or slightly, I can try to impose the equation over a thin region more than the original shell. So the number of equations will exceed the number of unknowns. This unknown is only defined on the thin shell. But when you impose this equation, you impose this equation over a set of equations. So the equation is over redundant. Okay, when it's over redundant, then you have this thing. Okay? And then the equations can be shown to have no internal resonance. Okay. There's one way to but another way is to actually use what is called a combined field integral equation. And that is actually a very neat trick. In this very neat trick, the interior problem turns out to be a solution to an interior cavity with lossy wall. Okay, if you have an interior cavity with lossy wall, what is its resonance frequency?
Complex.
Yes?
Complex.
It has to be complex. Okay? So it will never be set up. Any leakage of energy inside will never set up any internal resonances. Because internal resonances are time harmonic. And your solution everywhere is time harmonic. So using the combined field integral equation, then you also set up an interior problem that's different and has a different physical meaning. Okay? Any other questions regarding this? So you can read up more on this in the textbook if you want to. I can give you more to read if you want to. But I want you to understand the physics of this and why it comes about and how you can avoid it. Okay? So I'd like to start talking about fast multiple method and also a multi-level fast multiple algorithm. Okay, I'd like to illustrate this in 2D because the ideas in 2D are essentially similar to the ideas in 3D. So once I understood the ideas in 2D, you can extend them quite easily to a 3D problem. So we can consider a 2D scattering problem where you have a surface, okay, and you formulate an EFIE or electric field integral equation. In the field, you will see things like EFI. EFI means electric field IE, okay, which means that you impose certain things like N cross E incident is equal to N cross the S prime G R prime dot J R prime. This is an electric field integral equation for a PEC. That you put currents on the PEC object and demand that the current produces a field that exactly cancels the incident field either on the surface of the scatterer, slightly outside it, or slightly inside it. That is okay because this current does not produce a field discontinuity. So whether you impose this equation for R equal to S plus or S minus is immaterial. Okay, S is the surface, S plus is the surface that's slightly outside, S minus is the surface that's slightly inside. This equation holds true whether you impose it either way. Okay? And let's do this for 2D. 2D ones, we're just assuming that we have X and Y, and then Z is coming out of the blackboard. Then I can write down an EFI, okay, that looks something like this, an EZ incident in 2 dimensions is equal to I omega mu naught. Sorry, it should be I omega mu naught somewhere. Because that is actually the electric field produced. Yeah. Should be there also. Okay. I assume that I have a free space Green's function operating on the current Gs that essentially is flowing in the Z direction. Okay, this is Js rho prime in Z direction. Okay? And this is an electric field integral equation, and when we convert this into an integral equation, we impose the fact that rho has to be also on S. So the unknown is defined on S, and the equation is also defined on S. So they are on the same support. And the Green's function in 2 dimensions is this one over here. K rho minus rho prime. Okay, that is the Green's function in 2 dimensions. And you can convert this into a matrix system by subspace projection method, like the method of moments, method of weighted residual, point matching methods, and all kinds of methods to convert this into a matrix system. So for instance, I can let Js, the unknown current, be expanded in terms of a basis set Ai, Ji, rho, I equals to 1 to n, where this can be a pulse basis function, or it could be some other kinds of basis functions of your choice. Okay? And if you substitute that in, then this integral equation can become a matrix equation of this form. And once you test it, you can also test it. Bj, j is to 1 to n. You can convert this into a square matrix system. And if you use point matching, this AJI could be rather simple. You just test with the other function. You just test with the other function rho j, okay, I omega mu naught g naught rho minus rho prime, comma of ji rho prime. Okay, the matrix will be just something like that, where g naught is that Green's function defined over here, and I have chosen the testing function just to be a direct the other function because this integral exists. So this must be in the Dau space of this function over here. Okay, and I can choose this to be, for instance, a pulse basis. This is usually called a point matching method, because you impose this equation only at a certain finite number of points. You match that equation. So you can use other methods, of course. You have different systems, but the main idea is that we have a matrix system that's dense, which means that if I put a pulse basis over here to expand the unknown, this pulse basis is going to interact with every part of the scatter. Okay, this is I, this is j. Aij is always not going to be 0. Okay, how can we solve this dense matrix system fast? And it turns out that, as I showed you last time, one way of solving this dense matrix system fast is to do low-rank decomposition. We try to break this into a low-rank system, especially in the off-diagonal term. If you have off-diagonal part, you try to replace the off-diagonal parts with low-rank approximation. And then when you perform matrix vector product with those low-rank approximated off-diagonal elements, you can reduce the cost of a matrix vector multiply. Otherwise, the cost of a matrix vector multiply is ordered n squared, and that is too costly. Okay, we want to reduce this order n squared to something smaller. So factorization, matrix factorization is one way to do that. QR decomposition is one way to perform a matrix factorization. Say if you have a submatrix S that is only off-diagonal part, this is a matrix AS. You can do QR. Okay, and if this is, say, ns by ns, and if you make this to ns by m, and this m by ns, so when you do a matrix vector product with, say, a small vector as, then you can do it in a sequence like this. So the first matrix vector product is of course MNS. The second matrix vector product is of course NSM. Compared to the original one, it was NS to perform a matrix vector product. If you multiply a NS by say NS by MS vector, a matrix by the vector which is also of length NS, okay. The cost of performing this matrix vector product is that each row multiplied by each vector costs you NS. Okay, since the MS rows to do, the cost is MS times NS in performing the matrix vector product. Okay, you agree with that? Okay, so if you can do a low rank approximation such that M is much less than NS here, then this cost is much less than this cost. Okay, this cost is much less than this cost, and you can perform a matrix vector product. But this is not the only way to do matrix vector factorization. I mean, matrix factorization. You can get the matrix factorization analytically. Okay, and let's see how we can factorize the matrix analytically. And you will have to use the addition theorem. Or at least my way of showing it is to use the addition theorem. Okay. And the addition theorem says that if I have a Green's function, a Bessel function of order m, that describes a wave that emanates from this point. Okay, this is outgoing cylindrical wave, a cylindrical harmonic of this kind. So this describes a wave that is emanating, say, from this point O double prime. Okay, and they can describe this as being equal to a distance rho prime from the origin. This is the original coordinate system. This is my original coordinate system. And this wave is actually emanating from this point rho prime, so you can imagine a cylindrical wave emanating from here. Okay, that's what this means. And I'm observing the field over here at coordinate rho. Okay, so this distance is just rho minus rho prime. And the cylindrical wave is emanating from this point in this manner. Okay, and then describe my phi double prime to be this angle over here. If this is my x double prime, this is x and y, this angle over here would be phi double prime. So this is a cylindrical harmonic described about that point over there. Yes?
Can you think of addition theorem as like equivalence, some sort of equivalence theorem or equivalence principle like thing?
I don't think so. I think I asked you to do this in 3D, right? So I'm going to show you the simpler one in 2D, but you don't use the equivalence principle.
No, but isn't the idea similar? Like you're using a superposition of charge of sources somewhere else
Okay.
to represent the same field, right?
Okay, but not surface sources though.
Okay, yeah.
I'm replacing this field generated from here with a whole bunch of multipoles coming from here. Okay, so if I were to write this addition theorem in 2D as you have done in 3D, I will have this dichotomous behavior that depending on where my observation point is, I will have this kind of expansion n minus n phi prime, and then I will have this cylindrical harmonics in phi. Okay, this is in phi. So this part is the cylindrical harmonics that is about this point over here, about the origin which is phi and rho. Okay, and then these are the coefficients that I should use to make this equality work. And you have derived this coefficient before in 3D. The derivation in 2D is very similar. This is if you are outside this circle. This circle is in here. This is the circles of radius rho prime. Okay. If I draw a circle using this as the origin, and my circle is not very good. Okay. My circle is not very good. But you can imagine you take this rho prime and sweep it out and draw a circle. That circle will have radius rho prime. If I'm outside that circle, this picture is valid, which means that I only have outgoing waves. This is an outgoing wave. So the physical picture you get is that outside the circle, I only have outgoing waves, even though the fields are emanating from this point. Okay. Outside there, the field must satisfy radiation condition. It must be outgoing. Hence, I can only have this outside thing. And the other dichotomous property of this addition theorem is that if I'm inside the circle, I have to swap the two. Phi prime, okay? Phi prime in this angle over here. This angle is the coordinate system of this rho prime, so this is phi prime. Okay? Phi prime kn k rho e to the I n phi. And this, as I have learned before, and you have learned before, is a standing wave. Bessel functions are kind of a standing wave. So if I am inside that circle, if I'm inside a circle, I cannot use Hankel wave. I can only use Bessel wave to expand the field, because first of all, there couldn't be a singularity there. At rho equals to 0, the solution must be regular. Since the source is actually over here, okay, at rho equal to 0, the solution must be regular. Hence, this cannot be a Hankel function. Cannot be even the Hankel function the second kind. So the solution inside here must be expanded in terms of Bessel function. It's the only way. We have a number of choices to pick the solution here. And then when you match boundary conditions from the inner circle to the outer circle, you get these coefficients correctly. Okay, this is the addition theorem. So can you see the physical picture? You have a bunch, you have a source, a multipole source, emanating from this point. What it says is that outside the circle, you can pretend as if the multipole sources are located here. So this is a whole bunch of multipole that are outgoing, and they are all emanating from this point. Okay, these sources seem to be emanating from this point. If you're outside this circle, if you're within this circle, you can think of this that the source that produces a field there can make pretend as if it's producing a standing wave in this region, and the standing waves are oscillating about this point, in and out about that point. So it changes the coordinate system of the wave from one coordinate system to another coordinate system. If you look at the outgoing wave picture only, it changes the coordinate system of the outgoing wave that is emanating from this point to a bunch of outgoing waves that are emanating from that point. Okay, so it has this dichotomy. Okay, and you have to be aware of this. Any questions before we move on?
Sure.
Yes.
When you talk about multipole, are you the order of the multipole is related to the m index on the Hankel function?
Right, right. This is a multipole. This is a multipole of high order. If you set m equal to 0, I would just have a monopole on the left-hand side. But m is not 0 here, so I can have a general order multipole. Okay, this addition theorem is valid for all order multipoles, and it exists for all order. Okay. There is another one too, that if I replace it with a Bessel function, if I have a replace it with a Bessel function here, okay, it turns out that if I replace it with a Bessel function here, this Bessel function does not satisfy radiation condition to begin with. So the solution outside does not have to satisfy radiation condition. This will become a Bessel function on the right-hand side. Okay? And this will also become a Bessel function on the right-hand side. So it turns out that these two expressions are actually the same expressions, if this is a Bessel function. So there's no dichotomous behavior for a Bessel function. We have this dichotomous behavior only for when I have a Hankel function. So everything will become a Bessel function here, a Bessel function here, if I have a Bessel function on the left-hand side.
So then what's the physical meaning? Because if you have Bessel function, it's a standing wave, right?
This will be a standing wave about this point.
Yeah, so
Okay.
if my right hand side was, if my left hand side was a Bessel function,
Right?
then then your right hand side also a Bessel function.
It's
So,
also a standing wave.
it is a standing wave for all of rho.
Yes, all of rho is what the addition theorem says. Okay, the right hand side actually, this becomes one expression that looks like this. Okay, there's no division between larger than or less than anymore. Okay, you can write them as such. Okay, the right hand side just becomes that. Because there couldn't be singularity anywhere. There couldn't be singularity anywhere. Okay? And you can go about deriving this identity too. One way to look at it is that since this is singular, I have to have singularities on the right hand side. If this is regular, I have to remove those singularities on the right hand side and they become Bessel function. That's a quick way of deriving it. It's not very rigorous. You can also go through much more details, expanding this in terms of J's and modern functions and W and then mesh singularities. They see that you come up with the same expression. Okay. Another way to think about this is that
No, because idea, so inside the circle there should be a standing wave. That's fine. But if I had a standing wave for all of rho,
right.
that's something.
Okay. Let's see how you can convince you that the wave has to be standing everywhere.
Is it like when resonance is set up,
Yes.
where you don't need a source, but you still have standing waves everywhere?
Very similar. Very similar to that. That's a good point. It's very similar to that because this solution actually does not correspond to a source-driven solution. There's no source to drive this solution. This is a resonant mode. Okay, this is like a resonant mode solution. If you take the Laplacian of this, it does not have any data functions produced. So you have a standing wave emanating from here. It turns out that it can only be replaced with standing wave everywhere, not outgoing wave or incoming wave. Okay, that's a good point. And if you're not convinced of that, another way is to go through the mathematical derivation. But mathematics doesn't show you much insight, right? So how can I argue that this is also true?
Use Fourier somehow, Fourier analysis.
You can show by Fourier analysis as well. You can show that. Okay, you can show it by mathematics. Okay, you show it by mathematics. Many ways. But that is true. Okay, that theorem is true. This theorem is true. Okay. I guess you have to accept it. I can't prove it mathematically. It takes too long. Okay. So, however, I want to write this addition theorem in a compact form. I'm going to put everything I have into a column vector. Since this is indexed by m, you can think of it as a column vector. In a compact form, I can write this addition theorem as consisting of this. Beta rho prime. So I can think of this column vector as a matrix times another column vector. I can think of this as a matrix times a column vector. Okay? So the right hand side is just a matrix times a column vector. I can write it as such. And that is the upper part of the addition theorem. I can also write the bottom part. Bottom part, this is a dominant solution. I will call it the regular part of the Hankel function, because if you take the regular part of the Hankel function, you get the Bessel function. Hankel function consists of a singular part also, Hm1 is equal to Jm plus Imn. Sometimes we call this I. This term is singular. If you take the regular part of this, then it has to be that part. So let me just call it the regular part of this. Okay? And then multiply by this. This alpha is this matrix. This is my alpha matrix. Alpha nm. This is my beta nm. Okay, you can think of this as the matrix here, a matrix there. And they can write the solution as such. And then the third one, I can think of it as the regular part of the left-hand side being equal to the regular part of this. Okay, this can be thought of as regular part of this column vector times the beta matrix. Okay, notice that this matrix is also beta nm. Okay, plus this piece over here. So the regular addition theorem can be thought of as just taking the regular part of this equation.